Welcome to this exploration of one of the most fascinating paradoxes in food science, the Soufflé Stability Paradox. Today we're going to understand why fat, which normally destroys foams, actually helps a chocolate soufflé rise to incredible heights. Let's start with the fundamental problem. In basic kitchen physics, fat is the enemy of foam, but somehow chocolate soufflés need cocoa butter to reach maximum rise. How is this possible? First, let's understand what happens when fat meets foam under normal circumstances. When you're whipping egg whites into a meringue, even a tiny drop of egg yolk can ruin everything. Why? Imagine tiny air bubbles surrounded by protein films. These proteins create a stable network. But when fat droplets enter, they disrupt this delicate structure. The fat is hydrophobic, and it destabilizes the protein interfaces, causing bubbles to collapse. The fat droplets literally rupture the thin protein films that surround each air bubble. This is why careful cooks say never get any yolk in your egg whites when making meringue. Let's look at the physics. The stability of a foam bubble depends on surface tension and the Laplace pressure. Delta P equals gamma times the sum of 1 over R1 plus 1 over R2. Here gamma is the surface tension, and R1 and R2 are the principal radii of curvature. For a spherical bubble, both radii are equal, so this simplifies nicely. Delta P equals 2 gamma over R. This tells us the pressure difference across the bubble interface depends on surface tension and bubble radius. When fat molecules disrupt the protein interface, the surface tension gamma drops dramatically. Lower surface tension means lower pressure difference, and the bubble becomes unstable and collapses. Let's put some numbers on this. For a pure egg white foam, the surface tension is relatively high. The surface tension for protein films is approximately 50 millinewtons per meter. This creates stable bubbles. But when fat contaminates the interface, the surface tension drops to around 20 millinewtons per meter. That's less than half the original value. This means the pressure difference supporting the bubble drops by more than half. The foam structure collapses under its own weight. Now here's the paradox. A chocolate soufflé contains significant amounts of cocoa butter, which is pure fat. By our reasoning, it should be impossible to create a stable foam. Yet chocolate soufflé rise magnificently. What's going on? The answer lies in a complex interaction between sugar, proteins, and chocolate that creates what we call the sugar-protein-chocolate matrix. This matrix fundamentally changes how fat behaves in the system. Imagine a three-dimensional network. The sugar and proteins create a rigid scaffolding structure. The fat droplets become trapped within this matrix, and the air bubbles are protected by multiple layers of structure, not just a thin protein film. There are three key components that work together to create this paradoxical stability. First, sugar. When you heat sugar with proteins, it creates a highly viscous continuous phase. This viscosity is crucial because it slows down all molecular motion. The viscosity of the sugar-protein matrix is approximately 100 to 1000 Pascal seconds. Compare this to water, which is only 0.001 Pascal seconds. This is extremely viscous. This high viscosity is critical. It prevents the fat droplets from migrating to the air-water interfaces, where they would normally cause damage. The fat is essentially immobilized within the matrix. Second, the chocolate particles themselves. Cocoa powder and chocolate contain solid particles that create mechanical reinforcement. These solid particles create a framework, almost like the steel beams in a building. They provide mechanical strength that helps support the structure during and after baking. Third, protein denaturation. As the soufflé bakes, the egg proteins denature and form a gel network that locks everything in place. Protein denaturation occurs at temperatures between 60 and 80 degrees Celsius. This is exactly the temperature range inside a baking soufflé. The denatured proteins form covalent crosslinks through disulfide bonds. This creates a permanent gel structure that maintains the foam even as it cools. Now let's look at the thermodynamics. Why doesn't the fat destroy the foam even when present? The key is understanding interfacial energy. In a normal foam, minimizing interfacial energy drives fat to the air-water interface where it causes destruction. The interfacial energy equals gamma times A, where A is the interfacial area. The system wants to minimize this energy. But in the Soufflé matrix, the high viscosity and solid particles create kinetic trapping. The fat droplets cannot reach the interfaces because they cannot move through the viscous matrix fast enough. The diffusion time tau equals eta r squared over kBt. When this diffusion time is much greater than the baking time, the fat stays trapped. Here, eta is viscosity, r is the distance to travel, kb is Boltzmann constant, and T is temperature. Let's actually estimate this diffusion time with real numbers. Let's say viscosity is 500 Pascal seconds, and the fat droplet needs to travel 100 micrometers to reach a bubble interface. At baking temperature around 350 Kelvin, kBt equals 4.8 times 10 to the negative 21 joules. Plugging in these values, tau equals approximately 1 million seconds. That's about 11 days. But the baking time is only about 20 minutes, or 1200 seconds. The fat simply doesn't have time to migrate to the bubble interfaces before the protein gel locks everything in place. Let me give you an analogy. Think of the difference between a traffic jam and an open highway. In a normal foam, fat droplets are like cars on an open highway. They can quickly move to wherever they want, which is the air-water interface. But in a soufflé matrix, it's like a massive traffic jam. The fat droplets are stuck and can't move anywhere. Another analogy. Imagine trying to catch flies. In air, flies move freely and are hard to catch. But if you put them in honey, they're completely immobilized. The soufflé matrix is like honey for fat droplets. Now let's talk specifically about cocoa butter and why it actually helps the soufflé. Cocoa butter is special because it has unique crystallization properties. It can exist in 6 different crystal forms, called polymorphs. Form 5, the most stable form, melts at about 34 degrees Celsius, just below body temperature. This is why chocolate melts in your mouth. During baking at 180 degrees Celsius, the cocoa butter is completely liquid. But here's the key. As it melts, it actually helps plasticize the sugar-protein matrix. Plasticization means the matrix becomes slightly more flexible. This is counterintuitive. But this flexibility allows the air bubbles to expand more during baking, giving greater rise. The final volume is proportional to the baking temperature, divided by the effective surface tension. The cocoa butter slightly reduces the effective surface tension of the matrix, allowing greater expansion. Here's an interesting question. If cocoa butter helps, why doesn't adding other fats like vegetable oil help? Why does that destroy the soufflé? The answer is that other fats don't have the same crystallization behavior. Cocoa butter's unique polymorphism means it provides structure as it cools. Other liquid oils remain liquid and eventually do migrate to interfaces, causing collapse. Let's look at the mathematics of how bubbles expand during baking. From the ideal gas law, the volume ratio equals P1T2 over P2T1. Pressure and temperature determine how much the bubbles expand. As the soufflé bakes and temperature increases from room temperature to baking temperature, the air inside wants to expand significantly. Going from 20 degrees to 180 degrees Celsius, the volume ratio is 453 over 293, approximately 1.55. The bubbles want to expand by 55% just from temperature. But there's more. Water in the batter evaporates, creating steam. Steam generation adds far more volume increase than just thermal expansion of air. When liquid water turns to steam at 100 degrees, it expands by a factor of about 1700. This is the main driving force for soufflé rise. The sugar-protein chocolate matrix must be strong enough to contain this massive expansion without rupturing, yet flexible enough to allow it. This is where the cocoa butter plasticization helps. Let's estimate the forces involved in a rising soufflé. The pressure inside a bubble exceeds atmospheric pressure by roughly 1,000 pascals. This is the pressure trying to expand the bubble. The stress in the matrix, which is force per unit area, is approximately 10,000 pascals. The matrix must withstand this stress without breaking. Remarkably, the sugar protein gel has a yield stress right around this value. It's strong enough to contain the expansion, but weak enough to allow it. Evolution, through generations of recipe refinement, found this perfect balance. Here's another question. Why does a soufflé fall when you remove it from the oven? Understanding this helps us understand the stability. When you remove the soufflé from the oven, the temperature drops rapidly. The steam inside the bubbles condenses back to liquid water, which occupies far less volume. The volume ratio is about 1 over 1700. The bubbles lose most of their volume, and the soufflé deflates. A perfectly baked soufflé has just enough gel strength to maintain some structure even as it deflates. It doesn't collapse completely, but it does sink significantly. So let's resolve the paradox completely. How does fat help rather than hurt? Fat is helpful only when it's kinetically trapped in the sugar-protein-chocolate matrix. In this trapped state, it provides plasticization without destroying bubble interfaces. The timing is absolutely critical. The protein gel must set before the fat droplets have time to migrate to bubble interfaces. This requires precise temperature control during baking. Think of it as a race against time. Initially, fat droplets can move freely. As heating continues, the matrix becomes more viscous, slowing fat movement. Finally, the gel sets, permanently trapping the fat before it can reach and destroy the bubble interfaces. Let's look more closely at the chemistry of how proteins lock the structure in place. Two thiol groups on cysteine residues react to form a disulfide bond. This reaction is promoted by heat and slightly acidic conditions, exactly what we have in a baking soufflé. Each protein molecule can form multiple crosslinks with neighboring proteins. This creates a three-dimensional network, like a molecular cage that locks everything in position. The number of crosslinks increases exponentially with temperature according to the Arrhenius equation. EA is the activation energy, R is the gas constant, and T is temperature. The optimal baking temperature balances two competing processes: bubble expansion, which requires high temperature, and controlled gelation, which can happen too quickly if too hot. What are the practical implications of understanding this science? First, temperature control is absolutely critical. Too hot, and the gel sets before maximum expansion. Too cool, and the structure never sets properly. The optimal baking temperature is approximately 180 to 190 degrees Celsius. This gives the right balance of expansion and gelation kinetics. Second, sugar concentration matters enormously. Too little sugar and the matrix isn't viscous enough to trap fat. Too much and the matrix is too rigid to allow expansion. The optimal sugar concentration is approximately 20 to 30% by weight. This gives the right viscosity and gel strength. Third, the type of chocolate matters. Dark chocolate has more cocoa solids and less sugar, requiring adjustment to total sugar content. Milk chocolate has more sugar and less cocoa butter, changing the matrix properties. This Soufflé paradox has broader significance in food science, beyond just desserts. It beautifully demonstrates the difference between kinetic control and thermodynamic control. Thermodynamically, fat should destroy the foam, but kinetically we can trap the system in a metastable state. Many foods rely on similar kinetic trapping. Mayonnaise, for example, is kinetically stable, even though thermodynamically it wants to separate. The key is creating conditions where the timescale for reaching equilibrium exceeds the timescale for consumption. This principle appears in materials science too. Metallic glasses are formed by cooling alloys so fast that atoms don't have time to arrange into crystalline structures. They're kinetically trapped in an amorphous state. For those interested in advanced topics, the soufflé batter exhibits fascinating non-Newtonian rheology. The shear stress, tau equals tau 0 plus k, times the shear rate to the power n. Here tau 0 is the yield stress, k is the consistency, and n is the flow behavior index. For soufflé batter, n is less than 1, meaning it's shear thinning. It flows more easily when stirred, but resists flow when at rest. This helps in two ways. The shear thinning behavior allows easy folding of ingredients during preparation, but the batter maintains structure when poured into the dish. Once in the oven, the yield stress helps maintain bubble separation. Here's a fun thought experiment. Could you make a chocolate soufflé in zero gravity on the space station? This tests our understanding. The answer is yes, but it would look very different. Without gravity, there's no buoyancy-driven drainage. The foam would be more uniform, but might not rise as dramatically, since there's no gravitational force to oppose. Let's state the final, complete resolution of the Soufflé Stability Paradox. Fat kills foam through interfacial disruption when it can reach air-water interfaces. This is thermodynamically favorable, but requires molecular transport. The Soufflé sugar-protein-chocolate matrix creates such high viscosity that fat transport is kinetically blocked. The diffusion time exceeds the baking time by orders of magnitude. Meanwhile, the cocoa butter provides a plasticization benefit that helps bubble expansion. It's helpful precisely because it cannot reach the interfaces to cause harm. Finally, thermal-induced protein gelation locks the structure permanently before kinetic barriers break down. The timing must be precise. So the paradox is resolved. Fat doesn't violate the rules of foam stability. Instead, the Soufflé S-complex matrix chemistry creates conditions where fat is prevented from doing its normal damage while still providing mechanical benefits. It's a triumph of kinetic control over thermodynamic driving forces. Let me summarize the key scientific principles we've explored today. Surface tension governs foam stability. Lower surface tension means weaker bubbles, which is why fat normally destroys foams. High viscosity creates kinetic trapping that can override thermodynamic preferences. This allows metastable states to persist long enough to be useful. Multiple components work synergistically. Sugar provides viscosity, chocolate provides structure, proteins provide gelation, and fat provides plasticization. No single component could achieve this alone. Timing is everything. The sequence of gelation, expansion, and structure setting must occur in precisely the right order for success. Understanding the science doesn't just satisfy curiosity, it makes you a better cook. When you understand why temperature matters, why sugar concentration matters, and why timing matters, you can troubleshoot problems and even innovate new recipes.